Hi everyone. In this movie, I want to introduce a concept that will probably be new for all, or at least almost all of you. And that is the concept of thermodynamics specifically. And this equation I have on the slide here, delta G equals delta H minus T delta S. And in Chem 1, I want to give you a good qualitative understanding of what this equation means. So what are the variables in this equation? What do they mean? What does it mean if each of these variables is positive? What does it mean if each of them is negative? We're not going to do too much quantitatively plugging in actual numbers, but more along the lines of what does this mean if this variable is positive or negative? What does it mean if that variable is big or small? And here I'm going to try to introduce these concepts by giving you some examples of processes, both physical and chemical, that you're familiar with that correspond to different components of this equation. So let's begin. So the first variable I want to talk about is this first one here, delta G. And you'll hear delta G referred to sometimes as Gibbs energy or free energy or Gibbs free energy. But in Chem 1, I'm really going to try to stick to just calling it delta G. And the key piece about delta G is that it tells us whether a process or a reaction can happen, whether it can be observed. And the word we use for this in chemistry is spontaneous or spontaneity. So you're often probably used to thinking of the word spontaneous as let's do something spontaneous, meaning let's do something right now, let's do something weird and wild right now. In chemistry, that's not the definition we use. In chemistry, spontaneous means observable, means something can happen. This definition makes no mention of time. So a spontaneous process could happen very quickly, it could happen slowly, it could happen over millennia. And the key thing to remember is if delta G is less than 0, if delta G is negative, then the process is spontaneous. Or observable. If delta G is greater than 0, so if delta G is positive, then the process is not spontaneous, or the reaction is not spontaneous. So one perhaps morbid example of this is me dying. I am going to die someday, so the delta G of my death is negative. Hopefully that will not be for a long time, decades I'm hoping, but it's going to happen, so the delta G is negative. Another example that's maybe a little bit easier to think about is a rock rolling down a hill. So take these two diagrams. In A, we have a rock high up on a hill. In B, we have a rock at the bottom of the hill. The delta G from going from picture A to picture B is negative. We can observe rocks rolling down the hill by themselves. The delta G from going from picture B to picture A is positive. So the reverse of any delta G negative process is a delta G positive process. So now this doesn't mean we can't imagine it. You can close your eyes and you can imagine a rock rolling up the hill by itself. We've got great imaginations, right? But you can't observe it. And so delta G of a non-observable process is positive. Beta A is positive. Delta G of a observable process is negative. So A to B, delta G negative. Next, let's talk about delta S. Now, the formal name for delta S is entropy. And the most useful comparison to what entropy is disorder. So you can remember the mnemonic I use is disorder, has an S in it, and delta S is entropy. So for processes where a delta S is greater than 0, delta S is positive, we have increased disorder. And when we have processes for which delta S is less than 0, so delta S is negative, then we have increased order. So for example, if we have a process where things are organized, in this case I've shown 10 green dots on top, 10 blue dots on the bottom, and if at the end of the process they look more like this, they are no longer ordered, so the delta S for that process is positive. And as long as we're talking about delta S, I should mention the T variable as well. And so T stands for temperature in kelvins. Since it's in kelvins, it's always positive. And the take-home message here is, okay, whatever the delta S, whatever the sign of delta S is, that term, the T delta S, is bigger, it carries more weight, shall we say, at higher temperatures. The last term in this equation is delta H, and the formal definition of delta H is enthalpy, or we sometimes say enthalpy to help differentiate it from entropy. But the mnemonics here is, okay, enthalpy has an H in the name, delta H, and this, the closest analogy for this is this stands for heat energy. So as for the delta H term and its signs, so when delta H is less than 0, so delta H is negative, we say the process is exothermic, or that heat is given off to the surroundings. The surroundings are warmed up by the process. Conversely, if delta H is greater than 0, so delta H is positive, and in that case, we say that the process is endothermic. What that means is that heat is taken from the surroundings, and that makes the surroundings cool down. So perhaps the easiest example there is, say, a campfire burning. When a campfire burns, the surrounding area heats up, so the delta H must be negative. Putting it all together for that campfire burning process then, so we know that the delta H of a campfire burning is negative. It's a negative number. We're not going to worry about the magnitude of that number in Chem 1. All we care about is it negative, is it positive. For campfire burning, surroundings gets hotter, it must be negative. Delta S. Well, does a campfire burning increase or decrease the disorder of everything? If you think about it, it increases the disorder. So delta S is positive. What do I mean by that? Okay, so you're starting from some wood and some oxygen in the air. And that wood, over the course of the campfire burning, it's becoming smoke and ash and carbon dioxide and water that's being spread all around into the atmosphere. So starting from a very ordered log into gas around the atmosphere means that it's a delta S positive process. And so overall, we're going to have a negative number minus t, which is always a positive number, times a positive number. So this whole term here, t delta S, is going to be positive. So this whole term here, t delta S, is going to be positive. And a negative number minus a positive number is, regardless of the orders of magnitude, has to be a negative number. So we know then that delta G is negative. And that makes sense, right? Because we can observe a campfire burning, and so delta G must be negative. So this was a lot of new information, some abstract information, but very important information. So in class coming up, we are going to practice looking at some processes, figuring out their delta G, their delta H, their delta S, and learning how to use logic to deduce, okay, if we know something's delta S and it's delta H, can we deduce its delta G? Or, if we know any of those two variables, can we deduce the third or not? And we will talk about this in the context of intermolecular forces and dissolution. So, tying it all together. Looking forward to it. Bring questions. I know you have them. I'll see you soon. Thanks.